Hello there, welcome back to Differential Equations by Alexander. Alright, so today we're going to talk about the Cauchy-Euler equation, and I'm just going to give you the theory on how to solve the differential equation, and then on the next video I'll give you some examples. So the Cauchy-Euler equation looks like this. In front of the y double prime you have ax squared, in front of the y prime you have bx, and in front of the y you have a c. And then the g function can be any function that you want. All right, so now in order to solve this differential equation, that you no longer just have numbers in front of the y and the y prime and the y double prime, you actually have functions of this specific type. To solve this, you're going to look at the homogeneous equation. So this is the homogeneous equation in gold. And now we're going to assume that the solution to this differential equation is of this specific format, where m is some number. And so now the question becomes what is that value for m? And so in order to figure out the m, we need to find the derivative of the y, which in this case is going to be m multiplied by x to the n minus 1. And now the second derivative, this becomes m multiplied by n minus 1, and then x to the n minus 2. All right, so we're going to plug that information into the homogeneous equation, and then what do we get when we do that? So we're going to get, let me see if I can write this down. So ax squared, and we have m n minus 1 x to the n minus 2, so, and then plus bx, and then this is going to be m x to the n minus 1, so my pen is a little inky today, and then plus c x to the m is equal to 0. All right, so if you look at the powers in this guy, so this is the power 2, and then this is the power n minus 2, and then this is the same base, and so when you combine this, it actually gives you the following. It's going to give you a m n minus 1 x to the m plus b m x to the m plus c x to the m is equal to 0. All right, so now we are going to assume that the x is not equal to 0, and so we can kind of get rid of the x to the m, and then the thing that we are left over with is the following. So let me actually put this in gray. So let's write down a m n minus 1 plus b m plus c is equal to 0. And if you simplify things, at the end of the day, you do a little bit of algebra, and then you're going to get the following thing. So you get a m squared plus b minus a m plus c is equal to 0. So this is very quick here. So let me just type it up here for you. And so the auxiliary equation that we get is the following. So we have a m squared plus b minus a m plus c. And then this is called the auxiliary equation, but we have to be careful that this is the auxiliary equation for the Cauchy-Euler equation. This is a little bit different than what we have done in the previous sections. This is the auxiliary equation for the Cauchy-Euler equation. All right, so now that we have that equation, how do we solve this quadratic equation? We need to figure out what the value for m is. And so what we do is we look at the quadratic formula. And if you were to plug that the correct numbers into the quadratic formula, this is what it would look like. Okay, so depending on what you have under the square roots, which is called the discriminant, depending on what you have under the square root, you're going to get three cases. So the first case is going to be where the m gives you two numbers. Okay, so for example, if you have m1 is equal to 2 and then m2 is equal to 3, just randomly choosing the numbers, then the solution is going to be y is equal to x to the second power and y2 is equal to x to the third power. So that's what this means. So this is the case when you actually get two real numbers from the quadratic formula. So this is what your two linearly independent solutions will look like, depending on what your m1 and m2 are. So that's the first case. Now, the second case is going to be whenever you have a repeated root. Okay, so you only get one number from the quadratic formula, and it's basically repeated. And so what that means is that your solution, the two linearly independent solutions are of this format, where you have x to the power m1, and then the second function is going to be x to the power m1, but you have to multiply by the ln of x. Okay, so that's, and then the way that we get this second solution is by the reduction of order that we talked about in the previous video. So reduction of order. All right, so that's the theory behind that. And then we have one more case here. So the third case is whenever we have a pair of complex numbers. So the I here does represent the square root of -1. And so this is the case where we have this alpha plus I beta and alpha minus I beta. And whenever you have this complex case, the quadratic formula gives you complex numbers, then your solution is going to be of this format. But you have to identify the alpha and the beta carefully. And so this is x to the power of alpha cosine of beta ln of x. And then this is x to the alpha multiplied by sine beta of ln of x. Okay, so this is a little bit more involved than the other question, the other type of equation that we dealt with, where we just had x to the alpha, actually e to the alpha x cosine beta x. Anyways, so these are your two linearly independent solutions. And so now we have solved the homogeneous equation. Okay. So this is your homogeneous equation. You assume the solution was of this format, and then you were looking for the value for the m. And depending on the quadratic formula, you have three cases. So case 1, case 2, and case 3. Case 3 is the complex numbers. And then depending on what case you are, you have solved the quadratic, you have solved the homogeneous equation. Now, when you move on to the big problem that we have in the very beginning, where we have a g function and not just a zero function, then we need to find the particular solution. And so for that, we need to use the variation of parameters. And then if you remember, once you have your complementary solution, which was the combination, the complementary solution is the combination of C1y1 plus C2y2. So once you have that, you technically have your y1 and then you have your y2. So for the complementary solution, for the variation parameters, you assume that the particular solution is of the following format: u1y1 plus u2y2. And then your goal is to figure out the u1 and the u2. But for the variation of parameters method, you have formulas to figure out what the u1 and the u2 are. And those are in terms of the Wronskian and then the things that look like Wronskians. All right, so you assume that you get that using the variation parameters. And then the last thing you have to do is you combine the two pieces. So you have your particular solution that you just found in the previous step. And then before that, you had the complementary solution. And so the combination of those two things will give you the general solution for the problem. And then that's how you solve the Cauchy-Euler equation. Okay, so this is, like I said, this is just a theory. And I wanted to give you the three cases that we want to consider. So 1, 2, and 3 different cases for the homogeneous equation. And then on the next video, I'm going to give you some examples on case 1, 2, and 3. And on a different video, I'll give you an example where you actually have to use the variation parameters. All right, so that's all I want to say about this. I want to introduce the Cauchy-Euler equation and then the three cases that we need to consider for the specific homogeneous equation. All right, so I'll see you next time.